All right, so today's goal is to solve equations. So you've learned about how all these exponent and radical things work. The place they show up is they show up in different equations and functions that we then need to be able to solve and to graph in order to use them in some sort of productive way. So this is an equation that you could solve from Algebra 1, okay? Again, I never say that in an insulting way. It's just remember you have some knowledge. Go find it. Pull it out, okay? What would you do in this case to solve this equation? Awesome. Okay, so first we would subtract 6. Somebody explain to me why he's choosing to subtract 6 from both sides. Why that choice, Jack? Good, it's not under the radical. So our purpose here is to get the radical alone at this point. So I'm going to subtract. So I'm going to have the square root of x plus 4 equals 1. Damien.
If we wanted to write the equation out, could we put 6 plus the radical of x plus 4 so it won't look like it's under the...
Sure. The 6 and the square root are two separate terms, and since it doesn't matter the order in which we do addition, right, that's the commutative property, that it doesn't matter if you do 3 plus 2 or 2 plus 3, it turns out to be the same. So you could absolutely rewrite it if you wanted. Like this. Sorry, my plus signs look a little wacky. Oops. As long as you keep the right positive or negative symbol with the right term. In this case, the 6 is positive because the plus sign in front of it. The radical is also positive because there's no negative in front of it. Okay? So either way. What do we do at this point? Zeke? Good. So we kind of want to, every time we're trying to get x alone, we're basically trying to do inverse operations. We're trying to do all the things that would undo whatever they did to x to get x back to just being x and not having all this other stuff attached to it. So in this case, x is under a radical. We would want to square both sides because squaring a radical will just give us the radicand, that part that's under the radical. And 1 squared is 1. And then what would I do? Damien? Subtract 4 from both sides. So I would have x equals negative 3. Okay? Is this good with everybody? Yes? Okay. Now, one thing you want to be careful of when you're working with radicals is you do want to check your answers. And again, we've gone through this before. There's like, I check my answers because I'm a good algebra student, and someone told me I should always check my answers so I have good habits. And then there's like cases in math where like you better check your answer or everything you did mathematically was fine, but because of the way the mathematics works, you might have actually made an answer that doesn't work, okay? For example, let's say that I said the square root of x equals negative 3, and so the first thing you guys wanted to do was square both sides so that x is not under the radical. I would get that x is equal to 9. If you plug that back into the original equation, does it work? Because is the square root of 9 going to equal negative 3? No. So sometimes when we square both sides, we create extraneous solutions because it takes away the positive and negative identity of the number. It just kind of makes everything a positive. That's great for us finishing and solving the problem, but it means that sometimes you've done everything right, but you've created something that's wrong. Does that make sense? So when you're working with radicals, you definitely want to check that the answer that you get actually works in the original form of the problem, okay? So when I plug negative 3 back in here, negative 3 plus 4 would be 1. The square root of 1 is 1, and 1 plus 6 is 7. Good, okay? But I do want to check. Not because I'm extra super thorough, but because if I don't check, I could very well get tricked into leaving something as a solution that's not. Sophia? You would exclude that solution. So if it was one solution and you plugged it back in and it didn't work, your one solution is no longer a solution, so what do you have? No solutions. If you had 2 solutions to a problem and one of them worked and one of them didn't, so you excluded the one that didn't work, you would now only have one solution, okay? So you just exclude it, okay? It's labeled as an extraneous solution, so if you see that vocabulary word used, make sure you understand. It will equal 9. But when I plug it back in, This is what the equation looks like, and the value of this is positive 3, not negative 3. So those two quantities are not equal. Okay? The square root of, no. It can only be plus or minus when you're given something like this, and you took the square root. You get plus or minus 3, and both of those work because if you plug them back in and square them, you get positive 9 in both those cases. But here, when I plug 9 back in, the square root of 9 is not negative 3. It's positive 3. Okay? All right. So how this is going to change for us is that problem was Algebra 1 based because it was a square root. So you know how to isolate a square root and square both sides to get the answer. So how it's going to change is index, because we changed index, right? What if the last problem we did wasn't a square root? What if it was like a fifth root? What would you have done to solve the problem? Fifth square it. Just take it to the fifth power. Totally right idea, but all we have to say is take it to the fifth power. So basically, if the radical had a different index, we would just raise the problem to a different power in order to accommodate that. Does that make sense to everybody? So you always used a power of 2 because you were always using a square root that had an index of 2. If you're now using a fourth root, you want to use a power of 4, a fifth root, a power of 5, etc. So in this case, you have the same idea going on because the power of 1/3 really means what? Not square root, cube root, okay? I'm actually not going to write it in this sense because I want to get you familiar with the exponent notation you're going to see. But you still want to do the same thing. So you basically want to isolate the exponential part or the part that would have been underneath the radical. So what's the first step we're going to take in this problem? New people. Quentin? Good. Add 5. 5 is not included in the exponential or radical part of the problem. So go combine it with the other constant part so we can work towards getting a solution. So we're going to have 6x plus 9 to the 1/3 power equals negative 2, add it with 5, 3. So instead of writing this as a radical, I'm going to keep using the exponents because I want to point out to you exponent rules that apply here also. So if we did write this as a cube root, how would we get rid of the radical with an index of 3? The power of 3, okay? We are going to use the power of 3. I just want to point out to you what that is also doing. If we're raising this whole thing to a power of 3, okay, with exponent notation, these two exponents will multiply each other. What is 1/3 times 3? 1. See how nicely that works? Just like how the cube cancels out the cube root. 1/3 times 3 makes an exponent of 1. Do we really need to write an exponent of 1 on our paper? No. So I just want to show you that what you're doing with radicals and what you're doing with exponents are the same thing, because sometimes it's actually more convenient to use the exponent notation. Okay? So this will be 6x plus 9 on the left side. And on the right side, 27. And then you would go ahead and finish solving this problem. So I'm not going to walk you through the rest of it because I think that you could get there. Now, I can still go check my x equals 3. But if I did every step of this problem correctly, I'm actually pretty certain that I don't have to plug it back in to check. Does anybody know why I just made this big deal in the last problem about plugging in and checking, and now I said, like, oh, I feel kind of certain that I don't have to do it as long as I did everything correct? Good. So the exponent is odd. So when I raise something to an odd power, is it going to take away any of the identity of the number, like the negative and the positive? No, it's going to keep it all with it, so there's not going to be any deceiving me there, okay? It's not going to do that whole thing where I square negative 3, and it looks the same as if I squared positive 3, and now you can't tell what it was, okay? With odd powers, it's a little bit easier to work with, okay? But when in doubt, what should you do? Check. If you're not sure, then you go and check, okay? All right. This one looks a lot like the first problem we did. Then why am I doing another example like this problem? Seems boring. Stephanie? Oh, okay, there's an x on the other side of the equation, not included in the radical. I know. It's craziness. So the work is actually not going to be any different, but the amount of work it is for you is going to be more. And then you guys, I know, what people expect of you these days is ridiculous. Okay, All right, so first step, based on the first problem we did, how are we going to solve this? New person, tell me what I'm going to do first. Elijah. Subtract 3. Good. Same idea. Isolating the radical or the exponential part. The only difference in this case is I can't actually combine x and 3 into one term. Right, next step. Square both sides? All right. See, this is where you have to actually do some work. Okay, so here, since the radical and the square are inverses, I get 5x minus 1. Here, what do I have to do to square x minus 3? CJ? Multiply x minus 3 times x minus 3. Am I going to end up with a binomial or a trinomial when I do that? Trinomial, very good. This is not just x squared plus 9, okay? You have to actually go multiply out x minus 3 times x minus 3 and use the distributive property or FOIL or whatever you like to refer to. All right, what kind of equation do we have here? An equation, a mathematical equation, very good. Okay. Okay, yeah. Classify it by its degree. Let me say it that way. 2, a.k.a. it would be called a quadratic. How do we solve quadratics? Factoring, quadratic formula, completing the square. All right? So get all the terms on the same side. Hope that it can be factored, right? Can it be factored? Yes. Thank goodness. Good job, Miss Stahl. If it couldn't be factored, though, I'm not going to freak out, okay? I might be sad that I have to do more work, but I'm going to get over it, and I'm going to do the work. And what am I going to have to do? Quadratic formula, or if you like completing the square, the numbers are nicely working. Yeah, they do have some information for me. Okay, so what are my solutions? Dylan. Good. X equals 10 and 1. Okay. Should I check them?
No.
Did I raise both sides of this problem to an even power? So let me ask again. Should I check them? Yes. Okay, I should. Especially when there's a variable on the other side. Remember when we solved absolute value equations and we were reviewing Algebra 1 stuff? Even then, when there was variables on both sides, there was this kind of like unknown because you didn't know what number was over there, that you don't really know what happened. So you should check for 2 reasons here. You have variables on both sides of your equations that you did something to, and you squared both sides, so if one of them was negative or positive, you don't know once you squared it. Okay? So let's go ahead and check both of them. So you guys check them on your paper. You should know how to plug in and check. Okay, so I checked 10. It worked.
Yes, it worked.
I'm not going to assume anything. I hear people just, oh, check this one, only check this one. No, you check them all. You don't know. No, 1 didn't work. Okay. So 1 is actually not part of my solution set. I will not write it down as a solution. If somebody had to have me label it with the correct vocabulary word, what is 1? An extraneous solution, okay? But if someone asks me what the solution of this problem is, the solution is that x equals 10, the only thing that actually worked.
Can you explain why the extraneous solutions happen?
Yes. So the extraneous solutions happen So these 2 problems are very different, right? But once you square both sides of these problems, they now look exactly the same. So extraneous solutions occur in this case. It's different for different types of equations. But in this case, because we're raising things to a power, and specifically when we raise them to an even power, it takes away whether the number on the other side was positive or negative and makes two different situations appear the same. And in one of these cases, the solution actually works, but in the other one, it doesn't. So you could have the setup where a radical is equal to a negative, and once you square both sides, it looks like it works. But let's think it through. Is the square root of any number going to compute to be negative? Not unless they had a negative in front of it. Okay? So it has to do with the fact that when you raise it to an even power, you lose whether the number is positive or negative, and it makes these two different situations look the same, where the solution actually only works in one of those situations. CJ? No, so not underneath the radical. So with underneath a radical with the I is a whole different world of complex analysis type of things in a different type of it's actually in a geometric situation, which we at this point don't have the skills to understand, but not from underneath the radical. So we've never done anything with I underneath the radical, okay? What we've done is said if I had a negative underneath the radical, the answer would have an I in it when I've simplified, but nothing about simplifying something that ends up being negative when you take the square root of it. We had stuff that you could square and get a negative with our imaginary numbers, but not square root, okay? All right. Okay, so why are we doing this example? You guys have the general idea. There's a lot more math. All right, Nishi. So what do you guys think you want to do in this case? Okay, square both sides. And the bummer about this problem is there's the 2, and the 2 doesn't belong inside of any of the radicals. So when I square, I have a lot of work to do here, okay? When I square the right, that's going to be nice. I'm going to get x plus 10, okay? But when I square the left side, think about it. This is what I'm doing, okay? So what are we really doing? So don't get freaked out by it. We're really just spoiling, right? So if you have to, you're going to write it like this. It's not hard. It just takes a long time, okay? You have to have patience. So 2 times 2 is going to give me 4. 2 times this radical is going to give me 2 times this radical. Okay? The radical times 2 gives me 2 times the radical. And the radical times itself gives me the stuff inside the radical no longer in the radical. Is that okay with everybody? Like rad 3 times rad 3 is just 3. Okay. All right, these are like terms. And this constant of 4 can be combined with this constant of negative 6, giving me a negative 2. And then there's an x. All right, that's nice. Okay. So I get on the left side x minus 2 plus 4 square root of x minus 6. There you go. All right, what do you think we want to do now? Yeah. Perfect. We still have a radical in our problem that still contains x underneath it. So we still are working to get that radical alone, which means I'm going to move the x and the 2 to the other side of the problem. So I'm going to get 4 times the square root of x minus 6. These x's cancel out. That's very nice. Equals 12. I would probably at this point do what? Yeah, divide by 4 will make my life a little bit easier before I square and make like big giant numbers here. So square root of x minus 6 equals 3. So I had to do some work right here, but after that, it's not so bad. Right? But it takes me like double the time to solve the problem because now what do I need to do? No, I'm not even done solving yet. I don't have x equals something. Squared. So I get x minus 6 equals 9, so x equals 15. Do you think I need to go check? Okay, not only did I have variables in multiple places, and not only did I square both sides one time, but then I squared them again. Yeah, I could have made a big mess and I might not even know. Where am I going to check my solution of 15? In the original equation, okay? It's very important to check it in the original equation. Okay, so on the right side, the square root of 25 is 5. On the left side, 15 minus 6 is 9. The square root of 9 is 3. And 3 plus 2 is 5. That's good. Okay. Are we all right with the fact that we're still doing the same things we've done before, just in like a more complicated situation? Okay, so same process, more work. Okay, more work doesn't mean harder. It means more time consuming, maybe. Okay. All right, last example that we're going to do today, please. All right, so we had exponent things. Somebody give me first step. Somebody that hasn't told me how to do anything yet today. Kara. Okay, good. Subtract the 4. We're working on isolating the power that contains x or the radical that contains x. So 2 times x minus 1 to the 4/3 power. I'm going to subtract 4 from both sides. 32. Next step. Somebody that hasn't talked to us yet. Kristen. Good. I'll divide by 2. Anytime that works out nicely, you definitely want to do that before you like take roots or powers, because then you're stuck with this extra number underneath there. All right, next step. Nishi. Okay, good. We can actually do 2 operations at once here. Remember how I was showing you guys when we were working with exponents? When this was a 1/3, I cubed it, and that worked out really nice because the 3 in the numerator and the 3 in the denominator, when multiplied together, made the exponent 1. But right now, if I just cube it, does it make the exponent equal to 1? No. What else do I want to probably do? Good. 3 over 4. Okay? And this is the same thing. And this is why we talked about our rational exponents yesterday and how they work. So we get x minus 1 on the left side because 4/3 times 3/4 just becomes 1. And on the right side, we have 16 to the 3/4. Okay, what are we really doing when we apply a 3/4 power to both sides of the equation? Zeke? Okay, and both of these things are really important. We are cubing, and we are taking a 4th root. Let me ask you guys something. You did a homework assignment earlier. When you got somewhere like this and you took the 4th root to solve both sides of the equation, what did you get as the solutions for x? Just 1? Good. You got positive and negative 1, just like square rooting both sides. Okay, 4th root, 6th root, both of them give you plus or minus. So I want, Zeke, tell us again what taking the 3/4 power means we're doing to both sides of the equation. We're cubing it and taking the 4th root. If we are taking the 4th root of both sides of the equation, what do we need to include when we calculate this number right here? Plus or minus, just like you would if you were just individually taking the 4th root. So exponents are super handy, but you cannot shut off your brain, because if you are doing a square root, 4th root, something with an even denominator, you're going to have more than one thing happening here. You're going to have your plus and your minus. Okay? What is 16 to the 3/4 power? So what's the 4th root of 16? 2. And then cube that, 8. Okay? All right. So 2 solutions here. X can equal 9, or it can equal -7. Right? So check. Plug them back in. Okay? If we plug back in 9, what's 9 minus 1? 8. 8 to the 4/3 power means the cube root of 8, which is 2, raised to the 4th power, 16. 16 times 2 is 32, plus 4 is 36. Good job, 9. Okay? All right, -7. Think it through. -7 minus 1. Not -6. -7 minus 1. -8. Good job. Okay. To the 4/3 power means cube root -8, which gives you -2. And then raise it to the 4th power, 16. 16 times 2, 32, plus 4, 36. Good. Okay. All right, so some key things for today. What are you guys going to have to be careful of when you're solving the equations? So raise your hands. I'll call on you. Give me some ideas. Some key things that if you were going to go home and do this, you're going to be like, oh, yeah, I can't mess that up. Awesome. Okay, checking solutions because you don't know if they're extraneous. Very important. Okay? Soraya. Good. Checking that you don't need a plus minus. So those are the most common errors that are made in this problem. The other errors that are made are usually just because we talked about how some of them are a lot of work. So sometimes people don't keep it neat enough or packaged enough to see where they're going with the work. But the main conceptual mistakes are not checking for the extraneous solutions or not including plus or minus. Somebody break it down for me. When do I have to include the plus minus? CJ? Okay, good. So anytime you take a radical of both sides of the equation that has an even index, so square root, fourth root, sixth root, eighth root, is it always going to look like you put a radical on both sides? This problem doesn't look like we put a radical on both sides at all, but we still used plus and minus. What in this problem represented that we took an even index radical on both sides of the equation? I see CJ's hand, but I'm waiting for someone new. What in this problem, what in my work, shows you that I needed to include the plus or minus because I actually took an even index radical of both sides of the equation? Okay, which part of that, Elijah? Good. Okay. All right. So that we had an exponent of 3/4, that the exponent was rational means it's really a radical in disguise, right? And the index of the radical is that denominator down there, that 4. Okay. Z? Yes. No, we didn't raise it. So in example 3, the radical that existed in the problem was an even index, but we did not take a radical of both sides. We squared both sides. That's not a radical because it's not a denominator of 2 and the power. So this power of 2 is what we did to both sides. This problem is different because it has a denominator. It's actually a radical. Okay? 3/4 power is a radical. A power of 2 is not a radical because it's just a whole number. It doesn't have a denominator that's an even power. Does that make sense? So in this problem, we used a radical because we took a 4th root because 4 was in the denominator of the exponent. Problem number 3, either you're looking at the 2 and saying it's an even index, but it's not a radical power because it doesn't have a denominator. Or you're looking at the problem, but we didn't put this here. This came with the problem. Okay?